Today we're going to start our lessons on our Introduction to Chemical Equilibrium, which is the first of a three-part series as we study what chemical equilibrium is and the applications to chemical equilibrium. One thing that I want you to remember is that no chemical reaction goes to completion. So if you were to mix two reactants and allow them to react and leave it alone, it would ultimately reach chemical equilibrium. A reversible reaction is a chemical reaction in which the products can react to reform the reactants. So you have basically reactants forming products and products reforming reactants. When we talk about chemical equilibrium, that's when the rate of the forward reaction equals the rate of the reverse reaction. And at that point, the concentration of the products and reactants remain constant with time. When we represent a chemical equilibrium, we use arrows going in opposite directions, as you see here. This indicates that the reaction is at chemical equilibrium. You want to refrain from using this symbol, which, if you remember from the bonding chapter, indicates resonance. So please do not use the resonance symbol. That is not acceptable when representing chemical equilibrium. One thing we need to be familiar with is called the equilibrium position. So if the products are favored in your chemical equilibrium, what we say is that the equilibrium lies to the right because the products are on the right-hand side of the reaction. If the reactants are favored in the chemical equilibrium, we would say that the reaction lies to the left or favors the left, and that's because the reactants are on the left-hand side of the reaction. So how exactly is equilibrium established? Well, consider a reaction between water vapor and carbon monoxide gas. Upon mixing them, eventually they will begin forming hydrogen and carbon dioxide. And it's initially the reaction is only going in the forward direction because at first the initial concentration of water vapor and the initial concentration of carbon monoxide, we would know their concentrations. And in this case, I'm saying that they're equal because we can control our initial concentrations of our reactants because we would prepare them. As soon as you mix them, they immediately begin to react. As the particles collide, remember collision theory, they would collide with proper orientation and proper energy to reach that activation energy needed to form products. So at first, you only have reactants. There's no hydrogen nor carbon dioxide present. Now, depending on the kinetics of the reaction, the rate of the reaction would determine how fast it actually would reach equilibrium. But soon after the reactants are mixed, what starts to happen is the concentration of the reactants decrease because remember, they're decreasing over time. If you think back to the rate expression, we talked about the negative sign meaning they're disappearing. And when we would write the rate expression, you would say negative change in the concentration of the reactants over the change in time. And then when we talked about the products, we said they were increasing. So we would always put a positive sign to show they're appearing, change in the concentration of the products over the change in time. Now, beyond a certain point, the concentration of the reactants and the products would no longer change. And that's when the rate of the forward reaction is equal to the rate of the reverse reaction. And so what happens at that point is equilibrium has been reached. So equilibrium would have been reached when the rate of the forward reaction equals the rate of the reverse reaction. Now, if you remember from the kinetics chapter, chapter 14, we actually looked at this exact graph. And this is the only portion of the graph that we looked at because we were considering the reaction where you have the decomposition of nitrogen dioxide, forming nitrogen monoxide and oxygen gas. And when we determined the rate law using method of initial rates, we did that because we knew the concentrations of the reactants started to decrease over time and the products were increasing over time. So why was it so important to measure the reaction rate at the very start of the reaction? Well, if we uncover the part that was just blacked out, you see that these all level out over time. So as we just said, eventually the concentration of the products and reactants no longer change. So they level out or they have reached chemical equilibrium. That's when the rate of the forward and the rate of the reverse reaction are equal. Now, the next thing we want to look at is called the equilibrium constant. The equilibrium constant is a capital K as opposed to the rate constant, which was a lowercase k. The equilibrium constant K, or Kc, sometimes you see it written as KEQ, where EQ means equilibrium. If you're using it in terms of just pressures, if everything's in the reaction is in the gas phase, you can see Kp for pressure. When you see the C, it's meaning you're plugging in just concentrations. But the law of mass action is based on experimental observation, and it describes the behavior of various chemical systems in solution, which means they're aqueous, and in the gas phase. So no solids or liquids. So for the reaction, Ja plus Kb is in equilibrium with Lc plus Md. We would write the law of mass action by writing K, which is your equilibrium constant, is equal to the concentration of the products raised to their respective powers, divided by the concentration of the reactants raised to their respective coefficient powers. Notice we have L and M. Here we have L and M, so you use the coefficient from the balanced equation. These are multiplied together, so are A and B multiplied together. Notice you have J and K, so these are the respective coefficient powers here. We would be plugging in concentrations in this case because these brackets mean concentration. We do not ever include pure solids or pure liquids in the law of mass action. Only aqueous, that would be concentrations. And if you were going to do it as in the gas phase, you could write the K. If they were all gases, K would be equal to the partial pressure of C raised to the L power times the partial pressure of reactant D raised to the M power divided by the partial pressure of reactant A to the J power times the partial pressure of reactant B raised to the K power. You would plug in the values to those brackets or pressures, and then that would allow you to calculate K. K is your equilibrium constant, and it is a unitless number. I know a lot of you will be excited about that. You don't have to worry about figuring out your units. It can be calculated for specific temperatures. We're going to use the law of mass action to write the equilibrium expression for this reaction and then calculate Kc. So this reaction is balanced. I've given you the concentrations. Let's first write our law of mass action. Kc would be equal to, now notice this is a liquid, so we're not going to include it. We have everything else as a gas. Since they've given us concentrations, we're going to write this in terms of concentrations. So concentration of NO2 to the fourth power divided by concentration of NH3 to the fourth power times concentration of O2 to the seventh power. Now in the next video, we will pick up here and solve. You go ahead and solve this, and then when you come back to the next video, we will see how you did. All we do now is substitute these numbers in from the data into our law of mass action, and that will be our K.